Peering at the debris from particle collisions that recreate the conditions of the very early universe, scientists have for the first time measured the force of interaction between pairs of antiprotons. Like the force that holds ordinary protons together within the nuclei of atoms, the force between antiprotons is attractive and strong. The experiments were conducted at the Relativistic Heavy Ion Collider, RHIC, a U.S. Department of Energy Office of Science user facility for nuclear physics research at Doe's Brookhaven National Laboratory. The findings, published in the journal Nature, could offer insight into larger chunks of antimatter, including antimatter nuclei previously detected at RHIC, and may also help scientists explore one of science's biggest questions: why the universe today consists mainly of ordinary matter with virtually no antimatter to be found. RHIC is the perfect place to study antimatter because it's one of the few places on Earth that is able to create the elusive stuff in abundant quantities. It does this by slamming the nuclei of heavy atoms such as gold into one another at nearly the speed of light. These collisions produce conditions very similar to those that filled the universe microseconds after the Big Bang, with temperatures 250,000 times hotter than the center of the Sun in a speck the size of a single atomic nucleus. All that energy packed into such a tiny space creates a plasma of matter's fundamental building blocks, quarks and gluons, and thousands of new particles, matter and antimatter, in equal amounts. The scientists found that the force between antiproton pairs is attractive, just like the strong nuclear force that holds ordinary atoms together. Considering they'd already discovered bound states of antiprotons and antineutrons, those antimatter nuclei, this wasn't all that surprising. When the antiprotons are close together, the strong force interaction overcomes the tendency of the negatively charged particles to repel one another in the same way it allows positively charged protons to bind to one another within the nuclei of ordinary atoms. In fact, the measurements show no difference between matter and antimatter in the way the strong force behaves. That is, within the accuracy of these measurements, matter and antimatter appear to be perfectly symmetric. That means, at least with the precision the scientists were able to achieve, there doesn't appear to be some asymmetric quirk of the strong force that can account for the continuing existence of matter in the universe and the scarcity of antimatter today.